My name is Marina Durfey, and my summer research is studying randomly packed discrete domains for bonded particle modeling of isotropic solids. I would like to thank my sponsor, Sandia National Laboratories. I would also like to acknowledge my mentors, Sam Martin and Dr. Marcia Cooper of the Dynamic Material Response Lab at the Texas A&M Turbomachinery Laboratory.
A little bit about me. I was born and raised in Boise, Idaho, and I will be a senior this upcoming fall at Boise State University. I am currently studying material science and engineering with a certificate in mechanical behavior of materials. I chose MSE because I have always had an interest in math, science, and how materials are made the way that they are. After graduation in May of 2024, I plan to find work in research for material behavior. Many materials exhibit isotropic elastic behavior and under severe stress states may also fracture. DEM is a great tool for simulating fracture but must also perform well when predicting isotropic elastic material behavior. Bonded particle modeling uses a discrete element method, DEM, where particles that represent a coarse-grained volume of material are bonded together in a network to simulate continuum material behaviors. Randomly packed discrete particle elements are preferred over lattice-placed discrete particle elements for their improved geometrical isotropy. In the randomly packed discrete domains of the study, I'm investigating the relationship of geometrical isotropy to mechanical isotropy with also the random packing seed and the total number of particles. This is relatively unexplored in the literature for bonded DEM simulations of solid materials. With my research, I am working on characterizing the consistency of mechanical isotropy. Most bonded DEM simulations are done to understand the behavior of these models in the elastic regime, where geometrical isotropy is looked at very heavily. Non-crystalline materials are more specific to my research because when the cube of material is rotated about an angle, there is a possibility for isotropy geometrically and mechanically. A few examples of these materials would be rocks, pharmaceuticals, and pyrotechnics. My research methodology starts by randomly packing particles in a large domain that have been compressed to a desired packing efficiency, which is achieved in LAMMPS. LAMMPS is a DEM and molecular dynamics package developed by Sandia. Once the domain has been created, a smaller virtual cube is extracted, and each discrete particle in the cube is bonded within LAMMPS. Each extracted virtual cube is then compressed along one set of opposing cube faces. After compression, Young's modulus and Poisson's ratio are calculated. In order to understand the relationship between mechanical and geometric isotropy, the virtual cube is extracted in different orientations. This is done to maintain a nearly consistent arrangement of discrete particle elements while modifying the geometrical relationship between the bonded network and the virtual cube faces. The independent variables of this research are the virtual cube orientation and seed value to initiate the random particle packing process. The seed value is generated randomly in the code. It chooses a number between 1 and 25,565 to generate different particles based on the seed. The extracted cube is then rotated in the theta and phi directions. The dependent variables of this research are the macro-scale Young's modulus and Poisson's ratio calculated from each virtual cube. The applied stress, sigma m, is computed by summing the force applied to the top face and dividing it by the cross-sectional area. Young's modulus and Poisson's ratio are computed with the applied stress, axial strain epsilon z, and lateral strain epsilon x. The controlled variables are domain size, microparameters of the bonds, and the particle coordination numbers, which determine the average bond length. For the project, I built 4 different size domains that each produced 20 seeds and then extracted 32 virtual cubes with orientations varying from theta and phi. This is a total of 620 simulations per domain. The computing portion of this research has all been done using LAMMPS version June 23, 2022, Update 2 on my local machine, as well as the Texas A&M High Performance Research Computing Cluster Grace. I used Python scripts for automation. In order to research mechanical isotropy, 4 different domains were created. Each domain was run using 20 different randomized seed values that went through the same angles. The data for each domain was analyzed as either a function of seed value or as a function of orientation for both Young's modulus and Poisson's ratio. With each cube orientation and different domain sizes, I assessed the mechanical isotropy as shown in the plots. The graph shows the 4 unique domain sizes that were used to assess the Young's modulus and Poisson's ratio. I started with a small domain of 4.5 units, 5.5 units, 6.5 units, and ended with a large domain of 8.5 units. As the domain gets larger and increases the number of particles, you can see a trend in the data where the variance of the data decreases. For Young's modulus, the data of the 4.5 domain has a variance of 3.3, the 5.5 unit domain has a variance of 0.4, the 6.5 unit domain has a variance of 0.11, and the 8.5 unit domain has a variance of 0.03. The same can be seen for the Poisson's ratio of the different domains. The variance decreases as the size of the domain increases and more particles are created. For Poisson's ratio, the data of the 4.5 unit domain has a variance of 2e negative 3, the 5.5 unit domain has a variance of 6e negative 4, the 6.5 unit domain has a variance of 3e negative 4, and the 8.5 unit domain has a variance of 1e negative 4. Looking at how the different orientations of the cube compare for Young's modulus, each orientation shows some variance between them, but again, decreases as the domain size increases. As each domain was created and tested, you can see how high the variance started and continued to decrease in the data just based on how much the y-axis scale changed. As you can see in the 4.5 domain on the top left, we have a y-axis ranging from 3 to 12. But as you go down to this 8.5 unit domain, we have a y-axis of 7.2 to 8.4. That shows that the variance definitely decreased. Looking at how the different orientations of the cube compare for Poisson's ratio, each orientation again shows some variance between them, but decreases as the domain size increases. In order to understand the geometric isotropy, all 20 seeds in each different domain size were analyzed by going through each bond in a set grid. The grid that was used was 11 by 11, which went from 0 to pi. The program ran through each bond that added bond vectors. Once the bond vector was created, it was turned into an angle, which was assumed to be equal to 0 to pi. All the domains show a high degree of geometric isotropy. It was expected that bonds near the top and bottom would have a smaller value than the ones in the center because we normalized using the area of a cell instead of the phi value of the bond vector. The surface plots seen here are a Cartesian representation of polar coordinates. The area toward the top and bottom of the graph gets smaller for the number of bonds that are there. The number of bonds for each domain varies at about 5%. While there are 2 regions that contain the most bonds, it should be noted that this is only an increase of 2% compared to the rest of the band at phi equals pi over 2. After analyzing all the data, we can confirm that there was mechanical and geometrical isotropy. As the domain size increases, more particles are generated and packed in, which reduces the influence of local imperfections, resulting in lower variance in the data. One big note is that there's little change in geometric isotropy depending on the domain size compared to mechanical isotropy. This indicates that the domain does not contain crystallized regions. It also illustrates the importance of quantifying mechanical isotropy in addition to geometric isotropy, as significantly fewer particles are required for a domain to be geometrically isotropic. Since I characterized the critical aspects of a randomly packed domain for modeling isotropic material behavior, I was able to choose a domain from the analysis and create a beam for testing. This research is an extension of work done by Remy 2019, except not in a lattice-place discrete domain. I applied a shear force of 10,000 newtons per particle in the x direction to particles within 1 diameter of the top face of the beam and fixed the location of the particles within 1 diameter of the bottom face. The same is true for the top of the beam. We applied the force over at the top region, but our calculation assumes it's perfectly at a single point. The blue curve shows the numerical fit of how the beam should deflect, and the orange curve shows the theoretical fit of how our beam performed. Overall, this is a pretty good result given the low particle count of the 4.5 unit domain. There is some softness that occurs towards the bottom of the beam, which can be seen right here in the graph. But this should average out if we add more particles to the beam. With more particles packed into the beam region, the results would have closely matched the theoretical results. I hope you enjoyed my presentation on studying randomly packed discrete domains for bonded particle modeling of isotropic solids. We were able to prove mechanical and geometric isotropy. Mechanical isotropy was due to the increased domain size as well as the increased amount of particles that the domain created, whereas the geometrical isotropy occurred across all domains and wasn't affected very heavily when there were more particles added. Thank you.